All right, everybody, let's talk about 9.2 tests about population proportions. So our conditions for these are going to be very similar to the one proportion Z confidence intervals. We have the random condition, we have the 10% condition, and we have the large counts condition. But you'll notice the large counts requires n times p naught and n times 1 minus p naught. And that's because we assume H naught is true when performing a significance test. We use the parameter value specified by the null hypothesis, denoted by P naught, when checking the large counts condition. For a test, use the null value P naught, not the sample proportion P hat, to check the large counts condition. That is, we need the expected counts of successes and the expected count of failures to both be at least 10. So here's an example. Read this before you move on. All right, so all three conditions have been met. We have a random sample of 50 students from the high school. 50 is less than 10% of the students at the large high school, and both the expected number of successes and number of failures are both greater than 10 if the null hypothesis were true. All right, let's talk about a test statistic and p-value. A standardized test statistic measures how far a sample statistic is from what we would expect if the null hypothesis H naught were true in standard deviation units. That is, the test statistic is equal to the statistic minus the parameter divided by the standard deviation of the statistic. And if you notice that that has the same form as a z-score, you're right, that's exactly the same thing as the z-score. So right here, if I had the hypothesis that p equals 0.8 and I had a statistic of p hat equals 0.64, that would translate over here to my test statistic of z equals negative 2.83 on the standard normal curve. And, well, it's covered up by the bar, but you can see the formula there in yellow. All right, so one sample z-test for a proportion, we're going to use this formula right here, and we can either have an upper tail test where p is greater than p naught, a lower tail test where p is less than p naught, or a two-sided test where p is not equal to p naught. Let's read this example and then we'll move on. All right, the sample proportion of students at this high school who use Instagram is 0.82, which is greater than the natural proportion of p equals 0.76. And so for part B, our test statistic is calculated using this formula. We have z equals 0.99, and we do a normal calculation, and we get 0.1611. And here is a sketch of our hypothesized sampling distribution if indeed p is equal to 0.76. All right, and for part C, because the p-value of 0.1611 is greater than alpha equals 0.05, we fail to reject H naught. We do not have convincing evidence that the true proportion of all students at this large high school who use Instagram is greater than 0.76. All right, let's do a complete significance test. We're going to follow a four-step process just like we did with confidence intervals. We're going to state, we're going to plan, we're going to do, and we're going to conclude. So we want to state the hypothesis you want to test and the significance level and define any parameters you use. We're going to plan, and that's when we're going to identify the appropriate inference method to check conditions. Do, if the conditions are met, perform calculations. We're going to give the sample statistic or statistics, calculate the standardized test statistic, find the p-value, and then for conclude, we're going to make a conclusion about the hypothesis in context of the problem. All right, so for an AP exam tip, you can use your calculator to do this, but if you do use your calculator, you need to report the test statistic Z and the p-value. I'm not going to show you that in this slideshow, but I will show you when we see each other in real life on Zoom. All right, read this example before we move on. All right, so we want to state we will test H naught P equals 0.55 versus H alternative, P is greater than 0.55, where P is the true proportion of all California residents who use Netflix using alpha equals 0.05. And our plan, we check the conditions, check, check, check. All right, let's do this. We have a p hat of 0.6. That's going to give us a test statistic of 2.46, which leads to a p-value of 0.0069. You can see our hypothesized sampling distribution, and it's an upper tail test, so we shaded right here. And in conclusion, because our p-value of 0.0069 is less than alpha equals 0.05, we reject H0. There is convincing evidence that the true proportion of all California residents who use Netflix is greater than 0.55. All right, another AP exam tip. When making a conclusion in a significance test, be sure that you're describing the parameter and not the statistic. In the preceding example, it is wrong to say that we have convincing evidence that the proportion of California residents who said they use Netflix is different than the advertiser's claim, apostrophe. The proportion who said they use Netflix is the sample proportion, which is known to be 0.60. The test is convincing evidence that the proportion of all California residents who use Netflix is different than the advertiser's claim of 0.55. All right, let's do a complete two-sided significance test. Read this before moving on. All right, so we state and we have P equals 0.46 versus P is not equal to 0.46, where P is the proportion of all households in this town that have an Amazon Prime membership. We will use alpha equals 0.05. Let's check the conditions. Check, check, check. We're going to do this. We have P hat, which is 0.5375, Z 1.39, and our p-value is going to be calculated by this, which can be calculated using 1 minus normal CDF, and we get 0.1645. And because our p-value of 0.1646 is greater than alpha equals 0.05, we fail to reject H0. We do not have convincing evidence that the proportion of all households in this town have an Amazon Prime membership differs from the report's claim of 0.46. All right, the power of a test. Researchers often perform a significance test in hopes of finding convincing evidence for the alternative of a hypothesis. Researchers make a type 2 error if they fail to find convincing evidence for H alternative based on the sample data. How likely is a significance test to avoid a type 2 error? We refer to this probability as the power of the test. Down here in green, the power of a test is the probability that the test will find convincing evidence for H alternative when a specific alternative value of the parameter is true. All right, let's read this example and then we will move on. All right, the solution: if the true proportion of all children like those in the study who would develop ADHD when given the new vitamin tablet is P equals 0.05, there is a 0.937 probability that the company will find convincing evidence for H alternative, which is P is less than 0.11. All right, and the relationship between the power and the type 2 error, they're basically complements of each other. The power is equal to 1 minus the probability of a type 2 error, or you could say that the probability of a type 2 error is 1 minus the power. And increasing the power of a significance test, the power of a significance test to detect an alternative value of the parameter when H0 is false and H alternative is true, based on a random sample of size n and a significance level alpha, will be larger when the sample size n is larger. That's the best way, in my opinion. That's like a natural way to increase the power. And these two are kind of artificial ways. That's the significance level alpha is larger, and also the null and alternative parameter values are further apart. Let's look at an example. Read this before we move on. All right, so for part A, use alpha equals 0.10 instead of alpha equals 0.05. What would that do? Increase the power. Using a larger significance level makes it easier to reject H0 when H alternative is true. Let's go back. Part B, if the true proportion is P equals 0.08 instead of 0.05, Well, we would decrease the power. It is harder to detect a smaller difference between the null and alternative parameter value when they're closer together. And then part C, use n equals 500 instead of n equals 200. That would increase because a larger sample size gives more information about the true proportion. And we know that a larger sample makes a smaller variability in the sampling distribution of p hat. All right, that's it. I know that went quick, but I hope that was helpful.